to take this quiz here so you guys can see how to answer some of these questions. I apologize if the audio is terrible. It's the best I can do with the equipment I have. And it just wants me to finish the test. I don't want to finish the test. I want to start over. Oh well, I guess I'll just go back in. I've already done some of these. So let me go back to the beginning. Or I can't go back to the beginning. Frustration is setting in. Let me submit this quiz. Yes. Yes. Okay. Now I'm going to go back to my quizzes and try again. I am ready to start. And I'm going to set up my window here so that I can actually keep my Excel spreadsheet going right next to me. And minimizing the window and making it smallish and making my quiz window biggish. And then I will also come in a little for you to be able to see. And then we'll go ahead and start that test. It's jumping around on its own for some reason. Okay. The table below displays results from experiments with polygraph instruments. Find the positive predictive value for the test. That is, find the probability the subject lied given that the test yields a positive result. All right, so it says here, I want the probability that the subject lied given that the test yields a positive result. So I'm only interested in people who have positive test results, which is the top row here. So I know that my answer is going to be out of the total in that top row. And I'll go ahead and copy this and paste it over. And what I'm doing is I'm adding up the total right here, which I know you can do in your head easily, but that's what we're doing right there, 55. So my answer is going to be 55 in the denominator, and in the top, it says the person lied. So now that I'm only interested in my top row, these people don't even matter, so I can just delete them. And I'm interested in how many of those lied, and that was 45 people. So my answer is going to be the 45 out of the total 55, which is 45 out of 55, which is 0.8, and it asked me to round to 3 decimal places as needed. So that's my answer for that. A research center poll showed that 79% of people believe that it is morally wrong to not report all income on tax returns. What is the probability that someone does not have this belief? Oh, that's the law of complementary events, isn't it? Yeah, so it's just going to be equal to 1 minus 0.79. So the answer is 0.21. Use the data in the following table, which lists drive-through order accuracy at popular fast food chains. Assume that orders are randomly selected from those included in the table. If one order, okay, that's important. Let's pay attention to that. If one order is selected, find the probability of getting an order from restaurant A or an order that is accurate. And then it's going to ask us if those events are disjoint. Okay, so really we're just being prompted to consider overlap here. I'm going to copy to the clipboard and I'll start a new sheet here. So that was sheet 1. We'll do another one right here. All right, so what am I trying to do here? I want the probability of getting an order from restaurant A or an order that is accurate. Okay. So how many do I have that are restaurant A? restaurant B, restaurant C, restaurant D, and how many are accurate? Okay, so I'm going to do accurate, not, and I'll do A, B, C, D, because I don't want to take up this much space. All right, so now I can see it better. Good. First of all, my answer is going to be favorable outcomes over total outcomes. So the total is the sum of all of these. That's my N. And then the numerator is going to be all of the favorable events, which are either accurate orders, which is all these people right here, or restaurant A. So this will be the sum of all of these and comma this one. So my answer, they wanted it to three decimal places, will be this divided by this. And let's just make sure it is I'll make it to more decimal places because I want to see more information. See how we didn't see all that information before we made it more decimal places? Got to watch out for that when using Excel to answer these types of questions. In fact, now I'm starting to wonder if I was having enough places shown here. I didn't think of that before. Yeah, it's fine. All right, so there's my answer. And using the addition rule, rule singular, that would have been the probability of restaurant A or accurate would have been equal to the probability of restaurant A plus the probability of accurate, and then minus, actually I don't need to be doing this in here, I'm just trying to let you guys see. Let me do it like this and clear those out. It's taking too many cells and it's getting weird. So I'm going to do, if you don't, like right now I don't want this to be a real equals, I don't want a computation, so I just put an apostrophe in front that makes it text. So what I want to say is that would be the probability of A plus the probability of accurate, because this is either one would be fine in this one selection, and that would be minus the probability of A and also accurate happening together in a single selected trial person subject. All right, so that is going to be P of A. So P of A, let me just do it like this. P of A is, what is it? It's accurate, restaurant A is 325 out of how many? The total, whatever that was, 1127. The probability of accurate, hold on, someone's at the door. Very important. I'm very important. I'm not joking about that. Yeah, you're not. But you have important things to do. Yeah. Thank you. Okay, so sorry about that. Some people just don't understand how important I am. All right, so then the probability of being accurate is actually the sum of all these. Oh, not all those, just these. And then also divided by the total, which I have right here. And then I have to also look at the probability of both happening together. which is equal to this one over, well, these, I mean, over the total. And just notice that if I hadn't thought about that and I just add up this plus this, I'm going to get a different answer. In fact, it's greater than 1, which means it's not even a probability. Remember to keep your eye out for that. If you have an answer that's above 1, when you're trying to answer a probability question, that's a problem. You did something wrong, most likely. And what you need to do is subtract off the doubly counted probability section, which is right there. So watch when I take that back off, subtracting this, I get the same, wait a second, that's not the same answer I got up here. Something's not right in Denmark. So this is, maybe I had it reversed. Oh, I know, because this is supposed to be all the people, all the restaurant A people, not just the ones that are overlapping. So I really should have been adding up everybody in that. So that should have been the sum of the restaurant A people divided by the total. Right, and so when I don't have the overlap subtracted off, I get this as an answer which is greater than 1. And when I subtract off the overlapping probability, I get the same answer as I got up here. All right, so now let's go. Events are not disjoint because it is possible to pick an accurate order from restaurant A. Assume that 800 births are randomly selected and 406 of the births are girls. Use subjective judgment to describe the number of girls as significantly high, significantly low, or neither significantly high or low. All right, so we're just using subjective judgment, which means you do your best to try to guess, your best educated guess. Okay, so let's see. 800 out of, wait a second, assume 800 births are randomly selected and 406 of the births are girls. Do you think that's significantly high or low or neither? Subjectively, I'm looking at that and I'm going, that's about half. Half, 400 girls, 406 girls out of 800, that's about half. So that doesn't seem significantly low or high to me. It's more than half, so it's not significantly high. So I will say, since it's close to half, I'm going to choose neither. The number of girls is neither significantly low nor significantly high. Use the data in the following table which lists drive-through order accuracy at popular fast food chains. Assume that orders are randomly selected from those included in the table. If one order is selected, find the probability of getting an order that is not accurate or is from restaurant C. Are the events of selecting an order that is not accurate and selecting an order from restaurant C disjoint events? Well, you know what? This is the exact same question that I just answered, and I don't feel like doing it again, so I'm going to skip it. Even though I'm going to get it wrong, I don't care. They're going to let me skip it? Seems not. I'm just going to say 200, and that they are not disjoint because it is possible to select an order from restaurant C and in an inaccurate order. In the game of blackjack, played with one deck, a player is initially dealt 2 different cards from the 52 cards in the deck. A winning blackjack hand is won by getting one of the 4 aces and one of 16 other cards worth 10 points. The probability, or the 2 cards can be in any order. Find the probability of being dealt a blackjack hand. What approximate percentage of hands are winning blackjack hands? Well, this one is actually quite an interesting question because it is both an addition problem and also a multiplication problem. So we will look at this in two parts. First of all, we'll figure out how many winning hands are possible. And then we will also figure out how many ways to get each of those winning hands. Okay? So how many winning hands are possible? Well, maybe I won't figure out how, yeah, I'll figure out how many. So let's say I want to win, right? So what do I have to do to win? I got to draw an ace and one other card that's a 10-pointer. And it says that the two cards can be drawn in any order and I'll still win. So that means I could also draw a 10-pointer and then, let me say it like this, and then 10-pointer, or a 10-pointer and then an ace. And I have to keep this in mind when I'm thinking about how many winning hands are possible, because that's two separate types of winning hands. So now I figured out two different types, and either one of these would be favorable. So in order to win, I need the probability of this first event, an ace and then a 10-pointer, added with the 10-pointer and then an ace. So that's my addition rule part of the problem. But now I need to figure out what each of these probabilities are before I apply the addition rule. So then I'll come down here and try to think about how many ways I can get, or rather than that, let's just say what's the probability? What are the probabilities of each hand, winning hand, that's possible? And this is also a question. So I have two possible winning hands. And then here I have what are the probabilities of each winning hand. So for the first case, that was hand number 1. Let's just look at hand number 1. That was going to be an ace and then a 10-pointer. And then I also have hand number 2, which was a 10-pointer and then an ace. Now this says that as I'm doing this, I have the regular 52 card deck, and I'm going to be dealt 2 different cards, which means without replacement. Okay, so that's good to know. So that means that for the first card to draw an ace, the probability of drawing an ace, okay, so what I want is the probability of ace and then a 10-pointer is going to be equal to the probability of an ace on the first draw and then times the probability of an ace or a T on the second draw. So given that I do have an ace on the first draw, right? So there's where my multiplication rule is going to come in. The probability of drawing an ace on the first is 4 out of 52. And I want that to be a number. Wait, something ain't right. All right, so this is supposed to be 4 aces out of 52 cards on the first draw. And then this one is supposed to be, and I'll even do this, 4 out of 52. And then for the 10-pointer, it's 16, but I already took out an ace, so now it's 51. All right. So when I multiply these, I'm going to get 4 out of 52 times 16 out of 51, which is that. And then when I do this part, it's going to be the probability of a 10-pointer times the probability of an eighth, given that the first one was a 10-pointer, which will be 16 out of 52 times 4 out of 51. It keeps trying to give me a date there. I don't want a date there. I don't know why it won't do what I want. 4 out of, oh, I know, because I put the, no, I don't know why. It's just not doing what I want to do here. I want a number. Sorry, I'm fiddling around with this so much. Let me put it in as text. All right, now, when I multiply these, it's actually going to give me the same thing that I got when I multiplied these up here, because if you rearrange the order of the numerators, it's still going to give you the same result. Just to prove it to you, I'll do it real quick. So if I do 16 out of 52 and then times 4 out of 51, it's going to give me the same exact probability, right? So in the end, what happens is I end up with double this probability, because I'm going to be adding the probability of the first hand, that's hand number 1, plus the probability of hand number 2. And then I have to consider, can I get a hand where I have received an ace first and then a 10-pointer? And can that same hand also be a result of getting a 10-pointer and then an ace? No, right? You're going to have one or the other occur, so there's no overlap here to subtract. So when I'm finishing this, my answer is going to be the sum of those two, or rather two times, basically 2 times this, right? But that's as a decimal, and the answer is supposed to be given as a fraction. It says type an integer or a simplified fraction. So I have to do some simplifying here. So if I have 16, let me look at these right here. That'll make it a little easier. So now I'm just trying to simplify. 4 goes into 52. That can be 1 out of 13, right? And then 13 is prime, 51 is prime. So this is going to work out to be 16 is equal to 16 out of that, whatever that is. Okay, so 16 over this times this. All right, so there's my reduced fraction, but remember, I'm going to get the same reduced fraction for my second hand. I'm going to be doubling that up. So when I double that up, it's going to be 32 over 663. That's going to be my final answer. And as a percentage, we just had it a second ago, 0.4, well, you got to make it into a percentage, so multiply that by 100 or move the decimal to the right twice and round it to 2 decimal places. So the answer is 4.83%. All right, now I have, what is this? Refer to the sample data for pre-employment drug screening shown below. If one of the subjects is randomly selected, what is the probability that the test result is a false positive? Who would suffer? Okay, so we are selecting one subject, right? So we're interested in picking one person out of this entire pack. And let me go ahead and copy this to the clipboard. Okay, so the subject uses and the subject does not use, did not use. And we're either positive or negative, a test result. All right, so the false positives, what does it say again? What is the probability that the test result is a false positive? Okay, so I'm looking for the probability of a false positive. Well, it would be helpful to define what a false positive is, or locate it in my table at least. So a positive would obviously be any of these, and one that is false would be someone who the test is saying the person used drugs, but it's false. If it's false, that means the person didn't use drugs. So that's these people here. All right, so then my answer is going to be 2 people out of the total in the entire sample. Now I did highlight the positives, but I cannot narrow down my sample to positives because there is nothing in here that says that I'm guaranteed to be selecting just from the pool of positive test results, right? This is not a given that type of question. This is an overlap type of question. So the total N, the total sample size, is the sum of all that. So my answer is going to be 2 out of the total, which is 2 divided by 73, which gives me this, and as rounded to 3 decimals, that would be 0.027. Now, it doesn't say 3 significant digits. That's why I'm literally going to 3 decimal places, even though this front one is not a significant digit. But you should know that if I ask you to give your answer on paper, for instance, as a significant, rounded to 3 significant places, you would actually go all the way to 4 to round this properly. Who would suffer from a false positive? Okay, obviously somebody who's really not using drugs and doesn't get the job because the test falsely says they were using drugs. Obviously that type of person would be suffering. So the person tested would suffer. Okay, that's a good start, because they would be suspected of using drugs when in reality they were not using drugs. Okay, that's the one. It's important to try to go through all of them though. The employer would suffer, no. The employer would suffer, no. The person tested would suffer, possibly because he or she would not be suspected of using drugs. No, that's the wrong one. Okay, so yeah, we made the best choice here. In an experiment, we have people use, I'm going to jump here. Find the probability of randomly selecting the student who spent the money given that the student was given 4 quarters. Okay, good. So I'm only interested in the people in this sample who, okay, so for part A, I'm only interested in the people who, given that the student was given 4 quarters. Also note that in part B, I'm also only interested given that 4 quarters, okay, given 4 quarters. So in both of these parts, the given assumption is that they had 4 quarters. So that means these are the people with the quarters. This is the one with a bill. Spent, kept, all right. So if I'm only interested in the people or the kids who got quarters, then I'm going to eliminate the rest. And the first part says for part A, I want the probability that the student spent the money given that they were given quarters, right? which is why I narrowed down my scope here. And the total in my narrowed scope is 51. So this is going to be 33 students spent the money out of 51 students in the total set of students who received quarters. And so when I give my answer as a decimal to 3 places, it will be 33 divided by 51, which is 0.647. Here, we want the probability that the student kept the money, given that the student had received 4 quarters. So B, the other way around, the probability that the student kept the money, not the other way around, but just, you know, now they kept the money. All right, so we're still out of the 51 that were given quarters, and 18 of them kept the money, which is 18 divided by 51, which incidentally is equal to 1 minus this because they're complementary events, right? What do the preceding results suggest? A student given 4 quarters is more likely to have spent the money, right? Yeah, because there's a higher probability. A student given 4 quarters is more likely to have spent the money. A student given 4 quarters is more likely to have kept the money than a student given a $1 bill. A student given 4 quarters is more likely to have spent the money than a student given a $1 bill. No, because we didn't even consider the $1 bill people. We were really only looking at the students who had received quarters. A student given 4 quarters is more likely to have kept the money. Okay, so it's A. In a computer instant messaging survey, respondents were asked to choose the most fun way to flirt. Where D is directly, the probability is 73%. If someone is randomly selected, what is the probability of not D? That they thought it was more fun to not flirt directly. So that should be 1 minus this, whatever, they're complements, right? So it's 1 minus this, so don't overcomplicate it. The notation, it's just trying to see if you understand the relationship here. So the answer is 0.27. And what's going on? Can I not move forward? Oh, I didn't answer this up here. What does P of D? The probability of randomly selecting someone who chooses a direct person encounter, no. The probability of randomly selecting someone who does not choose a direct in-person encounter as the most fun way to flirt. Is the probability of randomly selecting someone who did not have a preference in regards to, okay, no. And the probability of randomly selecting someone who did not participate, no. Okay, so it's B. I'm confident. Let event A be the subject is telling the truth, and event B is the polygraph test, indicates lying. And now translate this, the P of B given A. Okay, so A is the given assumption. So telling the truth is the given assumption. So whichever one of these say given that the subject is telling the truth is a good place to start. So I'm looking at the ones that say given the subject is lying. No, it's not going to be A. Given that the subject is telling the truth, it could be B. Given that the subject is telling the truth, it could be C. Given that the subject is lying, it's not D. So it's either B or C. Now let's take a closer look. What was event B? The polygraph test indicates the subject is lying. So out of these two, it should say the probability of lying, and that's C. In a genetics experiment on peas, one sample of offspring contained 367 green peas and 469 yellow peas. Based on those results, estimate the probability of getting an offspring pea that is green. Is the result reasonably close to 3/4 that was expected? Okay, so what? What's the probability of getting a green pea? Let's see. 367 green, 469 yellow. Okay. So then in my sample here, I have green peas, I have yellow peas, and then I have a total. So I had 367 green peas, 469 yellow peas, and the sum total of those is 836. What is the probability of getting a green pea? Well, that would be equal to the number of green peas divided by the total. And 3/4 is 75% or 0.75, right? So is it close? No, it's not. So 0.439 is the answer to 3 decimal places, and no, it is not reasonably close. When randomly selecting adults, let M denote the probability of selecting male. B is randomly selecting someone with blue eyes. What does P of M given B represent, and M given B the same? Are they this? Is that the same as B given M? Of course not. We know already. That's confusion of the inverse. They're not the same when you change the order of the notation. So we already know that the second part down here is either going to be answer B or answer D, because they both start with mu. But let's look up here first. What does P of M given B represent? Well, the B is the given assumption. So blue eyes is the starting point. So we first look at the ones that say, given that blue eyes has been selected. So this one has that right there. Okay, that's the starting assumption, given that blue eyes. All right, and I don't see any others. It looks like it's going to be this one, but let's read them all, each carefully. The probability of getting a male and getting someone with blue eyes. No, that's not the same thing. Given and are not the same. Okay, this is overlapping out of the entire total rather than starting off on the narrowed down sample, eliminating anyone without blue eyes. So not the same. B, the probability of getting someone with blue eyes given the male. No, male is not the given assumption. Probability of getting male or getting someone with blue eyes. No. So it is C. Okay, then it's one of these two. No, because P of B given M represents a probability of getting a male. Given that someone with blue eyes has been selected. No. If the M comes second here in the notation, that's the given assumption. So the given assumption should be that the person was male, right? So it's got to be this one, most likely. It has to be, because it's the only other one that starts with no. So it's that one. Done. Use the data in the following table. Which lists? Drive-through order accuracy at popular fast food chains. Assume the order of the randomly selected and include the table. If 3 different orders, whoa. And then. No, and then. This and then. So it's 2 and thens. Find the probability that they are all from restaurant C. And they're going to be different orders, which means we're not replacing them. So we're going to use the multiplication rule. Okay, so again, if you simplify, sometimes that's helpful. All right, now I can see better. So my grand total is the sum of everybody. Okay, so that's the grand total. And we want to know what's the probability of randomly selecting 3 different subjects, 3 different orders out of this entire box and getting all 3 of them without putting any back. All 3 of them are going to be from restaurant C. So we are going to do the probability of C and then C and then C and how many? C, C, C. All right, so on the first try, we have how many C's? What's the total number of C's? 336. So on the first try, it's 336 over 139, right? And then it's going to be 335 because we'll assume the first one is C, 1138 orders left to choose from, and then assuming the second one was C as well, 334 over 1137, right? So the answer is going to be the product or multiplying this times this times this divided by the product of this times this times this, and then whatever that is our final answer. This divided by that, and so we have to 4 decimal places, which is 3 significant digits, incidentally, 0.0255, that's 4, right? Yes. Okay. 3 of the 50 digital video recorders in an inventory are known to be defective. What is the probability of randomly selecting that a randomly selected item, so just one, is defective? Well, that would be 50, 3 of 50. Okay, so the answer is just 3 out of 50. Y'all, simple. Don't overcomplicate it. It's not in at least one question. It just says just one is being selected. What's the probability that the one you pick up is going to be defective? 3 divided by 50. That's it. Let me make sure I have enough decimal places here. All right, moving on. If radio station call letters must begin with either K or W and must include either 2 or 3 additional letters. Whoa, this is a very complicated question. How many different possibilities are there? Okay, if a radio station's call letters must begin with either K or W, let's try to map this out. So I'm going to just try to see what we can do here. We can do K as a starting first letter. It can be K or it can be W. Either of those would do. And then it must include either 2 or 3 additional letters. Okay, so either 2 or 3 additional letters. How many different possibilities are there? Well, it doesn't say we can't repeat any. It just says additional. It doesn't even say that we have to rule out K and W. So I'm going to assume that this problem was not poorly written, and I can go on exactly what it says. So I'm assuming that I have 26. So all the spots I have to fill, if I start with K, so I have 2 choices there, and I'm filling how many spots? I'm going to fill either 2 additional spots or 3 additional spots. Interesting, huh? All right, so let's see. I have 2 choices on the first one, and then either 2 or possibly, so I have these 3 spots to fill, or I could have 4 total spots to fill, where the first one has 2 possible choices, right? And then I have to fill 3 additional ones. And it doesn't say anything about with replacement, without replacement. It doesn't say I have to exclude K and W. So I'm going to assume that I have 26 available on each of my other selections. And that means that I can have 2 times 2 times 26 times 26. That was supposed to be a times. Or I could have 2 times 26 to the power of 3. And that since either way would be good, I'm going to add those together, right? Because the addition rule here, either one of these would be fine. And since this set has 3 letters and this set has 4 letters, there's not going to be any overlap because all of these are going to be different just because of the only 3 letters, and 4 letters here. So there's no overlap here. So I can just go ahead and add these. I don't have to subtract off the probability of an intersection because the probability of that happening is 0. So just adding up, I get this. All right, so let me double check what we're being asked to do here. Uh-oh, something's going on. There we go. All right, how many? There are 36,504 possibilities. And I don't know what else it wants. Oh, I'm done now. I'm going to submit the quiz. Okay, so I had an hour to do this. This took me 45 minutes. You want to get to where you can work this quickly. I was explaining it as I was doing it. I got a couple wrong here, so we'll look at those. But you know, you do want to be able to get these done quickly as you're moving through. While I'm explaining it, it's not as fast. I would have worked faster not explaining it, so keep that in mind. 0.818. What was I supposed to say? 0.8? Why? What's wrong with it? Okay, the table below displays results from experiment polygraph. Find the positive predictive value, which is the probability that the subject lied given that the test yields a positive result. Okay, so what I did is I only looked at positive results. Let's go back to the beginning. That was question number 1. And I did the total in my top here as 55. Given that the test yields a positive result. Okay, yes, that's 55, right? I'm not adding that wrong. It's 55. Okay, good. And then find the probability that the subject lied. So I needed that the subject lied. So the subject lied is all the people in this pile, 45. So the answer is 0.818. And oh, okay, so what happened here probably is that there were some hiding decimals, right? No, that's not what it is. What's going on? 45 divided by 55. 45 people that lied out of 55 positive test results. People voice raising, I'll find the positive predictive residence. That is, find the probability that the subject lied given that the test yields a positive test result. Yeah, I don't see any mistake here. Huh. Yeah, that's what I did. So 45 out of 55 should be the answer. So I believe there is something wrong with this question, actually. I'm going to have to look into that. 0.3.19. All right, what else did I get wrong? This one. What does this say? You answered 200. I did? I don't remember answering 200. That was the restaurant question number 5. Let's see. All right, so Well, I actually have different numbers here. Is that the same question? Oh, yeah. I forgot. I purposely answered that one wrong because I didn't feel like working it a second time. Yeah, this is a duplicate question, I believe. So let me write that down as well. Okay. All right. So what else did I get wrong? Anything else? Question 13. You answered 0.0255 and that's wrong. Why? Why is it wrong? Is this the numbers? That's not the numbers either. Huh. Maybe it was, oh, this is the one that came up. Oh, it's the same type of scenario, but different question. There we go. 312, 279, 246. Okay, cool. So I got that wrong somehow. So how did I get that wrong? Did I not add up all? See, my grand total was B2 through D through E3. Okay, got that. All the people, I was asked to find the probability they're all from C. And what did I do? Oh, I see what I did. I looked at this C instead of this C. So the answer should have been the 284. All right, so my answer should have been this, which is yes. Okay, so just be careful that if you have A, B, and C in your top, what are they called? Labels of your columns. Just watch out that you don't mix them up with these up here. Okay, so other than that, good job, Professor Stevens. And I'll have to find out why that other question was marking me wrong because it's wrong, not me. So hopefully that helped. Tomorrow we're having a quiz, and this is just being sent out as a last-minute little extra tippy top that you can possibly benefit from if you are in the habit of checking for announcements and updates on a regular basis, and or you are making sure you get your alerts to your phone because you downloaded the Blackboard app or the Outlook app for your emails. And with that, I will see you tomorrow. Best of luck. I really hope you guys do well. Take care.